Hello everyone, this is Lakshmi. Welcome to my channel Lakshmi Lucky. Yeah, we are discussing in linear algebra previous question papers January 2023 right now. So we did already some problems ma, and one more problem I am discussing. Let B1 has given 1 minus 3, B2 is minus 2 4, C1 is minus 7 9, C2 is minus 5 7. And consider the basis for R square given by B is B1 B2, C is C1 C2. In this, the find change of coordinate matrix from B to C. Okay. So in this we need to find change of coordinate matrix from B to C by using B1 B2 C1 C2. And bases are nothing but has given B is nothing but B1 B2, C has given C1 C2. These two are bases for R square. Okay. So now let the matrices given matrices B1 B2 C1 C2, and capital B has given B1 B2. This is basis for R square, and C has given C1 C2. These two are basis for R square only. Now we are considering the matrix C1 C2 B1 B2. So we need to find change of coordinate matrix from B to C right now. So we need to reduce the matrix in the form of I over P. That means I is nothing but identity matrix, 2 by 2 matrix, 1 0 0 1, and P is nothing but normal form. Okay. So by using row operation only, not column wise just will apply row operation by using echelon method. Matrix B to C, it should be is equal, right, in the column wise C1 is nothing but here minus 7 9, and C2 is minus 5 7, and B1 is 1 minus 3 right here, and B2 is minus 2 4. Just for verify variation, just I am taking here line. Okay. And we are changing R2. Second row we are changing, not R1. Okay. So R2 to R2 you should multiply with 7. R1 is multiply with 9. Okay. So R1 we are not changing, right, as it is here. Okay. Minus 7, minus 5, 1, minus 2. And in the second row we are we are changing, no. So 9 means 7 9s are 63, 9 7s are 63 minus 63 should be 0. Okay. And 7 7s are 49, 9 5s are 45, minus 45 plus 49 we should get 4. Okay. And 7 3s are 21, minus 21 plus 9, minus 21 plus 9 is minus 12, and 7 4s are 28 plus 9 2s are 18, minus 18. 28 minus 18 is 10. So after reducing in the second row this element we are getting this matrix. Again in the second row I am dividing R2 is dividing by 2. Okay. So R2 is divided by 2 means R1 as it is you should write minus 7, minus 5, 1, minus 2, 0. Divided by 2 means 2 we should get, minus 12 by 2 means minus 6. This is 5. Okay. And now I am changing R1 only. R1 to 2 R1, because here 2 is there, here 5 is there So 2 R1 plus 5 R2 I am taking, because here minus is there, that's what I am taking here plus. Okay. So R2, R1 you should multiply with 2 only 2 7s are 14, minus 14 plus 0 means minus 14 only, and 2 5s are 10, minus 10 plus 10, this is 0, and 2 1s are 2 plus minus 6, 5 6 are 30, 2 minus 30 is minus 28, and 2 into minus 2, minus 4 plus 25, minus 4 plus 25 is 21. Okay. So here we can divide with, because identity matrix we need to form right now. So my dividing by minus 14 R1, and R2 is dividing by 2. Okay. Then we should get minus 14 is divided by 40 minus 14, it should becomes 1. 0 is there, and minus 28 is divided by minus 14 is 2. 14 2s are 28 right now, and 21 means minus 3 by 2. Okay, and 0, 2 by 2 is 1, and minus 6 by 2 is minus 3, and 5 by 2 we should get. So 1001 is nothing but what, identity matrix. This here P is nothing but normal form. 2 minus 3 by 2 minus 7 by 2 5 by 2. This is the change of coordinate matrix. B to C, from B to C is nothing but 2 minus 3 by 2 minus 3 5 by 2. Okay, note this one. Yes, now we are discussing in 14th problem, B bit first one. The statement has given here, if V1, V2, V3 so on V are eigenvectors that corresponding to distinct eigenvalues lambda 1, lambda 2 so on lambda r has given of M by N matrix A. So then we need to prove here the set V1, V2 so on Vr is linearly independent. Okay, so suppose here the statement here, these are vectors and corresponding eigenvalues has given lambda 1 to lambda r. In the matrix A, M by N, all are distinct eigenvalues. So we have to prove that here this set is nothing but linearly independent right now. Anyway, here suppose V1 to Vr is nothing but linearly dependent set will take. Okay, and one of the vector dependent set means any one of the vector is nothing but linear combination of preceding vectors. So that means P is nothing but index such that Vp plus 1 is nothing but linear combination of its preceding vectors we are taking. That means we need to take it should be exist scalars right now. So then there exists C1, C2 so on Cp. These are scalars, and such that this Vp plus 1 can be written as linear combination of remaining vectors C1, V1 plus C2, V2 so on Cp, Vp. Okay, and multiplying on both sides here by A and using that fact A Vk is nothing but is equal to lambda k Vk. We are using A Vk is equal to lambda k Vk, where k is nothing but 1, 2, 3 so on. A V1 is equal to lambda 1 V1, A V2 is equal to lambda 2 V2, like etc. we can take. Anyway, we obtain here A Vp because we are multiplying with on both sides A, no? So A into Vp plus 1 is equal to A into C1 V1 plus A into C2 V2 so on A into Cp Vp. That only we are writing here. C1, C2 are constants. These are scalars, right? No? So that's what I am taking inside. C1 into AV1 plus C2 into AV2 so on Cp into AVP. Because we have these values, because by using this condition AVK is nothing but what is there? Lambda k Vk. Instead of k, I am saying no, 1, 2, 3 you should substitute. So lambda p plus 1 Vp plus 1, because here A Vp plus 1 is there na. By using this condition lambda k Vk means lambda p plus 1 Vp plus 1 we can write it should be is equal to C1 into AV1 means lambda 1 V1 plus C2 into lambda 2 V2 plus C3 into lambda 3 V3 plus so on Cp into lambda p Vp. Okay, they make this equation 2. Here equation 1 is there, and here multiplying this equation 1 with lambda p plus 1, because here on the left hand side lambda p plus 1 Vp plus 1 is there. Now we can equate both the equations. Okay, for that purpose I am multiplying with lambda p plus 1 for this equation. Okay, lambda p plus 1 into Vp plus 1 is equal to C1 into lambda p plus 1 V1 plus C2 into lambda p plus 1 into V2 so on Cp into lambda p plus 1 into Vp. Okay ma? So make this equation 3. Here from equations 2 and 3, not 1 and 3 ma, 2 and 3 you should take from these two, because here second equation we have on the left hand side lambda p plus 1 Vp plus 1, and the equation 3 on the left hand side lambda p plus 1 Vp plus 1. Right now both are equal, so we can equal to equate into right side conditions RHS conditions. So this condition RHS from the second equation is equal to RHS from the third equation. So here you should take on the left hand side all these terms. We should get minus terms. So that's what here C1 and B1 we can take the common. Remaining lambda 1 minus lambda p plus 1 plus C2 into lambda 2 minus lambda p plus 1 into V2 plus so on. Cp into lambda p minus lambda p plus 1 into Vp is equal to 0 we should get. That means here this total term is nothing but constant, scalar. So linear combination of vectors. Linear combination of vectors V1, V2, V3 so on, Vp are there. Since we have V1 plus V1, V2 so on, Vp, these are the linear, this is the linearly independent set, right now? Yeah. So the weighing in the above equation all are zeros right now, but none of the factors lambda 1 minus lambda p plus 1 are zeros. This should be 0 means because eigenvalues are distinct are there right now. So hence C1, C2 linearly independent means each scalar must be equal to 0. So C1 equal to 0, C2 equal to 0 up to Cp is 0. That means Ci equal to 0 means we write from 1 to P only. But from equation 1 Vp plus 1 equal to 0, which is impossible. If Vp plus 1 equal to 0 means dependent means it should be not equal to 0, because here all scalars should be equal to 0 means vectors must be not equal to 0. So here it should be 0 means which is impossible condition, which is absurd. So therefore given set is nothing but not a linearly dependent set. It is not a linearly dependent set means it should be V1 to Vn is nothing but linearly independent set only. Okay, this is very important theorem. Okay, note this theorem, and thank you so much for watching my video.